Welcome back to another episode of Second Career Pilot.
Good to be back.
Today, we're tackling a cornerstone of aviation, really getting under the hood of our flight instruments.
That's right.
You've brought in some excellent reference material, and I think our aim today is to dissect the really critical aspects, especially for those of you listening who already have some flight experience but want to sharpen that understanding.
Exactly. We're going to zero in on, the systems that feed us that essential flight data.
Okay.
I think the pitot-static setup, the sensitive altimeter and its potential errors, which are pretty important.
Oh, yeah.
And also the fascinating world of gyroscopic instruments,
Mm-hmm.
all absolutely vital, especially when visual references aren't available.
For sure. Instrument flying relies on them completely.
And we'll touch on some of the newer digital stuff that's making its way into GA too.
Great. Okay, let's jump straight into the pitot-static system.
Yeah.
It feels like the bedrock for some fundamental readings.
It really is. Your airspeed indicator, your altimeter, and the vertical speed indicator, the VSI, they all rely on it.
Right.
The key thing to remember, though, is that static pressure is used by all three, but only the airspeed indicator needs that pitot pressure, the ram air.
Got it. So how does the plane actually sense these different pressures? Seems pretty clever.
Well, the pitot pressure comes from that tube facing forward right into the airflow, captures the ram air.
Yeah.
That pressure goes straight to the ASI or maybe an air data computer in newer planes.
And static.
Static pressure is just the ambient air pressure around the aircraft. It's sensed through small holes, static ports, flush on the fuselage usually.
Mm-hmm.
Somewhere the air isn't disturbed much. Often you'll see two, one on each side.
Ah, why two?
Helps cancel out errors if the aircraft is slipping or skidding sideways a bit.
Yeah.
Gives a more average, accurate reading.
Makes sense. And I've noticed those ports in the pitot tube sometimes, they look like they can be heated.
They often are, yes. Essential for anti-icing. You absolutely cannot have ice blocking those openings. It's critical, especially in icing conditions, obviously. Keeps the readings accurate.
Yeah, I can see how that would be a major problem. So what happens if, say, the pitot tube does get blocked?
Okay, if just the main opening gets blocked but the drain hole is clear, the airspeed might just drop to 0. But if both the opening and the drain hole get blocked, maybe by ice, or even insects trapped pressure, makes the ASI act like an altimeter.
Wow, okay, so climb, airspeed goes up, descend, airspeed goes down.
Exactly. Very dangerous. Very misleading.
Definitely disorienting. What about a blocked static port? That affects more instruments, right?
It does. A blocked static system messes with all three. The ASI will be inaccurate. It'll read low if you climb above where it blocked and high if you descend below.
Okay.
The altimeter just freezes, stops right at the altitude where the blockage occurred.
Yeah, the VSI.
Reads 0. Continuously, because it relies on sensing the rate of change in static pressure. If the pressure's trapped, there's no change.
So is there a backup for a blocked static system?
Yes, many aircraft have an alternate static source, usually a valve you can pull or switch inside the cockpit.
And where does that get its air from?
From inside the cabin or cockpit itself.
But the pressure inside isn't quite the same as outside, is it?
Yeah.
Due to airflow.
Precisely. Cabin pressure is typically a little lower than the outside static pressure.
So activating it causes, some slight errors?
Yeah, you'll see a slightly higher indicated altitude, a slightly higher airspeed, and the VSI will momentarily show a climb when you switch over. You need to know what to expect.
Good to know. Now, I've also heard about position error. That's separate from blockages.
Yes, even with perfectly clear ports, the airflow around them can get a bit messy in certain flight attitudes, like high angles of attack or with gear and flaps down.
Okay.
This can cause small errors in the ASI and altimeter readings. Manufacturers test for this, and the POH or AFM will have correction charts.
Important to check those for your specific aircraft, though.
Absolutely crucial.
Okay, solid overview of pitot-static. Let's shift to the sensitive altimeter itself. It's quite a piece of engineering.
It really is. Fundamentally, it's just a very precise aneroid barometer.
Aneroid, meaning no liquid.
Correct. It has these sealed, evacuated metal capsules, usually corrugated bronze. They expand and contract as the outside air pressure changes.
Right, like bellows.
Exactly. And that tiny mechanical movement is amplified through gears and levers to move the planers on the dial, showing altitude. Sometimes they stack multiple capsules for more sensitivity.
And we see different ways it displays the altitude.
Yeah. The classic three-pointer type needs careful reading, one for hundreds, one for thousands, one for 10,000s of feet.
Takes practice.
It does. Or you might have the drum type, where a pointer shows hundreds against a rotating drum for thousands. Easier to read at a glance for some.
And the absolute key step is setting the barometric pressure correctly in the Colesman window.
Absolutely critical. You dial in the local altimeter setting, QNH, usually in inches of mercury here in the US or millibars elsewhere. Adjusting that knob physically moves the pointers and the scale. Remember, 1 inch of mercury change is about 1,000 feet of indicated altitude change.
And that gives us indicated altitude, different from pressure altitude, right?
Correct. Pressure altitude is what you get when you set 29.92 inches or 113.2 millibars. That's our standard datum used for flight levels and performance calculations. Indicated altitude is your height above sea level based on the local pressure.
Okay. Now, like the pitot-static system, altimeters aren't perfect. They have potential errors too.
They do. First, there's a simple mechanical check. Before flight, set the current local altimeter setting and check that the indication is within usually 75 feet of the known field elevation.
Standard pre-flight item.
Yep. Then there are inherent errors due to non-standard atmospheric conditions. Temperature and pressure deviations from the standard model.
Let's talk temperature first. How does that affect it?
Okay, think about air density. Warmer air is less dense, so the pressure levels in the atmosphere are spread further apart vertically. So if you're flying at an indicated altitude of, say, 5,000 feet, but it's warmer than standard, your true altitude above sea level will actually be higher than 5,000 feet.
And colder air.
Colder air is denser, the pressure levels are compressed. So at the same indicated 5,000 feet in cold air, your true altitude will be lower.
Ah, and that's the one that really bites you for obstacle clearance.
Exactly. Extremely important in cold weather operations, especially in mountains or on approach. You could be significantly lower than you think.
So those cold temperature correction procedures are vital.
Absolutely. You don't correct ATC-assigned altitudes, but for charted IFR altitudes, like minimums on an approach, you must apply corrections when it's very cold, using tables like the ICAO cold temperature error table.
And you need to tell ATC you're doing that.
Yes, advise ATC if you're applying corrections to charted altitudes. The corrections can be substantial, hundreds of feet sometimes, especially at lower temperatures and higher procedure altitudes above the reporting station.
Okay. What about pressure errors?
That's the other big one. If you fly from an area of high pressure into an area of lower pressure without updating your altimeter setting.
High to low, look out below.
That's the one. Your altimeter assumes a standard pressure lapse rate. If the actual pressure is lower, it thinks you're higher than you really are. So your true altitude will be lower than indicated. Always get updated altimeter settings en route.
Got it. Now, for ATC to manage traffic, they need everyone on the same page, altitude-wise. That's where encoding altimeters come in.
Precisely. An encoding altimeter is connected to your transponder. For Mode C and Mode S, it automatically reports your pressure altitude, always referenced to 29.92 inches to ATC.
Ah, so it doesn't matter what I have set in the Colesman window.
Doesn't matter at all for the encoded transmission. ATC gets a standardized altitude reference from all Mode C-equipped aircraft, reported usually in 100-foot increments. There are accuracy standards, too, typically plus 125 feet.
And this standardized reporting is what allows for things like RVSM, reduced vertical separation minimum.
Exactly. Above flight level 290, RVSM airspace allows aircraft to be separated by only 1,000 feet vertically, instead of the older 2,000 feet.
Doubles the available altitudes up high.
Pretty much. But it requires specially certified aircraft with highly accurate altimetry systems and specific pilot training.
Okay, let's switch gears to gyroscopic instruments. Attitude, heading, turn indicators. These work differently based on gyros.
Right. They rely on principles of gyroscopes, two main ones: rigidity in space and precession.
Rigidity in space, meaning it wants to stay pointing the same way.
Exactly. A spinning gyro resists changes to its orientation. That's the principle behind the attitude indicator and the heading indicator. They maintain a stable reference.
And precession.
Precession is, well, if you apply a force to a spinning gyro, it doesn't react where you push it. It reacts 90 degrees ahead in the direction of rotation.
Okay, bit weird.
It is, but it's how rate of turn indicators work. A turn creates a force the gyro precesses, and that precession moves the needle or display.
And these gyros need power to spin really fast.
They do. High RPMs are needed for rigidity. Power usually comes from either a pneumatic system air pressure or vacuum, or an electrical system.
Pneumatic, like a vacuum pump.
Often a vacuum pump driven by the engine. Older, simpler planes might use a venturi tube on the outside. Multi-engine planes often use pressure systems for redundancy. Or They can be electrically driven, DC, or sometimes AC, requiring an inverter. Redundancy is key, often having both types.
Let's look at the attitude indicator, the AI or artificial horizon. How does that use rigidity?
The AI has a gyro spinning on a vertical axis. It's mounted in double gimbals, which allows the aircraft to pitch and roll around the gyro, while the gyro itself stays fixed relative to the actual horizon.
So the little airplane symbol moves against the blue over brown horizon display.
Exactly. The horizon bar stays parallel to the real horizon, and the little symbolic aircraft shows your pitch and bank relative to it. There are markings for bank angle and pitch degrees, and a knob to adjust the little airplane up or down for pitch trim.
And they take a moment to stabilize after startup.
Yeah, they have an erection mechanism to get them vertical, takes a few minutes, and they can have small temporary errors during things like rapid acceleration or deceleration, or after a 180-degree turn, but they self-correct.
Okay. Next, the heading indicator, or directional gyro, DGG, also uses rigidity.
Yes, but its gyro spins on a horizontal axis. It's great for showing heading changes smoothly because it doesn't bounce around like a magnetic compass.
But it doesn't actually know where north is, does it?
Correct. It's not magnetic. You have to manually set it using the magnetic compass as your reference.
Midriff.
Yes, due to the Earth's rotation and tiny imperfections, it precesses over time. You need to reset it to the magnetic compass roughly every 15 minutes to keep it accurate. Most common GAs are air-driven.
Gotcha. Okay, last of the classic 3 gyros.
Yeah.
The turn indicators.
Yeah.
2 main types.
Right. The older style is the turn and slip indicator. It shows rate of turn.
How's that work?
It uses precession. It has a gyro tilted on its side. When the aircraft yaws, like in a turn, the force causes the gyro to precess, tilting it, and that tilt moves the needle left or right to show the rate of turn.
And the bowl underneath. The inclinometer.
That just shows coordination. If the ball is centered, the forces are balanced a coordinated turn. If it slides left or right, you're slipping or skidding. The turn needle often has marks for a standard rate turn, usually 3 degrees per second, a 2-minute turn.
And the turn coordinator. What's different there?
The key difference is the turn coordinator's gyro is canted upwards, maybe 30 degrees or so.
Why?
This lets it sense both yaw rate and roll rate. So as you roll into a turn, it shows the rate of roll initially. Then, once established in the turn, it shows the rate of turn, like the turn and slip.
And it looks different, too. Usually has a little airplane symbol.
Yeah, instead of a needle, it has a mini airplane that banks to show the direction and rate. It still has the coordination ball underneath. Important note, neither of these gives you pitch information.
Right, no pitch information. Often written right on it. Exactly. Okay, that covers the classics. But technology hasn't stood still. We have things like AHRS now.
Right, attitude and heading reference systems. These are basically solid-state replacements for the mechanical gyros.
How do they work? No spinning bits.
Generally, no. They use things like MEMS, microelectromechanical systems sensors, accelerometers, rate sensors, and magnetometers, sometimes even GPS data, all processed by computer.
Advantages.
Much more reliable, lighter, less maintenance than spinning mechanical gyros. Ring laser gyros were an earlier type of non-mechanical gyro technology, too.
And alongside AHRS, we often see air data computers, ADCs.
Yep. The ADC takes the raw data from the pitot pressure, static pressure, and also outside air temperature. It computes precise airspeed, indicated true, altitude, vertical speed, and temperature, then sends that digital data out to the displays and other systems.
Like the EFIS displays.
Yeah.
Electronic Flight Instrument Systems.
Exactly. EFIS, or glass cockpits. Instead of individual analog gauges, you have large computer screens. Usually a primary flight display, PFD, and a multifunction display, MFD.
Big step up.
Huge. Lighter, more reliable, less power, easier to integrate information, very configurable.
So the PFD replaces the traditional 6-pack of instruments.
It does. It combines attitude, airspeed, altitude, vertical speed, heading, turn rate, all onto one integrated display. Much easier to scan. Many now offer synthetic vision, too.
Oh yeah, the 3D terrain view.
Right. It gives you a virtual picture of the outside world, enhancing situational awareness, especially in poor visibility.
And the MFD, what goes on there?
The multifunction display handles everything else, moving maps, engine instruments, weather data, traffic information, approach charts, terrain awareness warnings, lots of possibilities.
And they usually back each other up, right?
Yes, a key feature is redundancy. If one screen fails, the other can usually display the essential PFD information. Very important safety feature.
We're also seeing ADS-B becoming widespread. That ties into this.
Automatic dependent surveillance broadcast. Yes, instead of relying just on radar, ADS-B-equipped aircraft broadcast their precise GPS position, altitude, velocity, etc. directly to other aircraft and ground stations. Huge boost for traffic awareness.
And all this technology enables more safety systems, too.
Absolutely. Things like radio altimeters measuring actual height above the ground, crucial for low approaches. Traffic systems like TIAS, ground-based, or TIAS, airborne, like a simpler TCS.
TCAS being the big one.
Traffic Alert and Collision Avoidance System operates independently of ATC. TCAS-A gives traffic advisories, traffic. TCS-2 can actually issue resolution advisories, climb, or descend.
And terrain avoidance, GPWS and TAWS.
GPWS, Ground Proximity Warning System, was the earlier version, using radio altitude and other data. TAWS, Terrain Awareness and Warning System, is the modern standard. It uses GPS position and a detailed terrain and obstacle database to provide much earlier predictive warnings about potential collisions with terrain. Much better, especially in mountainous areas.
And head-up displays, HUDs, projecting info onto the windscreen.
Yep, HUDs project critical flight data like airspeed, altitude, attitude, and flight path guidance onto a transparent screen in the pilot's forward view. Reduces the need to look down at instruments, especially during critical phases like landing.
Wow. Okay, so with all these systems, simple or complex, the pre-flight checks are absolutely paramount.
Non-negotiable. You need a systematic approach. Checks before engine start, after engine start, and even during taxi.
Okay, run us through the key things before engines start.
All right, walk around. Check pitot tube clear, static ports clear, antennas okay. Check aircraft logs. Altimeter static check done, ELT battery okay. Check no TAMS. Inside, switches off. Suction gauge reading. ASI should read 0 ideally, or note the reading. Attitude indicator uncaged, level, set the altimeter to current setting, check against field elevation should be within 75 feet. VSI at 0, heading indicator uncaged, turn coordinator level, magnetic compass. Fluidate. Card moving freely, correction card present. Clock set. Engine instruments normal. De-icing anti-icing available. Alternate static source selector checked. Pitot heat switch off, but check the heating element if possible on walk around.
Comprehensive. And after engine start.
Listen for gyro spin up. Check suction gauge or electrical indicator show power to the gyros. Check magnetic compass again. Ensure it's moving freely. Let the gyros erect fully, then set the heading indicator to the compass. Re-verify the altimeter setting and reading. Check VSI is 0, tap gently if needed. Check engine instruments stable. Check radios. Test de-icing anti-icing systems if applicable.
Final checks during taxi.
As you turn, check the turn coordinator. Shows turn in correct direction. Ball moves opposite the turn. Check heading indicator against known taxiway or runway headings should be consistent within about 5 degrees. Check attitude indicator. Horizon bar stays generally level during straight taxi, maybe tips slightly in turns. And listen for any unusual noises from the instruments right up to takeoff, and even note how they spin down during shutdown.
Fantastic. We've really covered a lot of ground today, from the fundamental pitot-static and gyroscopic principles right through to the latest digital systems and safety tech. Hopefully this gives everyone a clearer picture of these vital cockpit tools.
Yeah, the accuracy and reliability of these instruments, well, they're just fundamental to flying safely. Those pre-flight checks, understanding the limitations, potential errors, it's all part of good airmanship.
Definitely. And it's a complex area. We'd encourage everyone to dive into their specific aircraft's POH or AFM and the Pilot's Handbook of Aeronautical Knowledge for even more detail. Maybe there are specific instrument aspects you're still curious about. Let us know.
Always more to learn.
Thanks for listening.